Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. The reaction shown is cyanohydrin formation, where HCN adds across the carbonyl C is equal to O of a ketone to give an alpha-hydroxynitrile, cyanohydrin. The mechanism proceeds via nucleophilic addition of CN to the carbonyl carbon. A catalyst for this reaction must be able to generate CN from HCN, i.e., it must be a base strong enough to deprotonate HCN, pKa 9.2, but should not be so strong or nucleophilic as to cause side reactions. Moving on to the next step. Identify what kind of catalyst is needed. The catalytic cycle requires a species that can abstract the proton from HCN to generate CN, which then attacks the carbonyl. The catalyst must therefore be a base with appropriate pKa. Moving on to the next step. Cl is an extremely weak base, conjugate acid HCl, pKa -7. It cannot deprotonate HCN, pKa 9.2. Cannot act as a base catalyst here. CH3CO, acetate conjugate acid CH3CO has pKa 4.75. Since pKa of CH3CO 4.75, pKa of HCN 9.2, acetate is not basic enough to deprotonate HCN effectively. It is a weaker base than CN. IChO, ethoxide conjugate acid ETOH has pKa 15.9. Since pKa of ETOH 15.9, pKa of HCN 9.2, ethoxide is basic enough to deprotonate HCN and generate CN. The generated CN then attacks the carbonyl to form the cyanohydrin, and the proton is transferred back, regenerating the base catalyst. ETO thus acts as a true catalyst in this reaction. HSO4, this is an acid, pKa 1.99, not a base. It would protonate CN and suppress the reaction rather than catalyze it. And for the final step, only ETO, option C, is a sufficiently strong base to deprotonate HCN and generate the active nucleophile CN, acting as a base catalyst for cyanohydrin formation. Therefore, the correct answer is C. Therefore, the correct answer is option C.